record. Okay, so hi everyone, welcome to the Probability Seminar from Chile. This time we have Marco Aymone from UFMG, Minas Gerais, who is going to talk to us about a random walking number theory. So yeah, all yours, Marco.
Okay, thank you very much for inviting me to give a talk here in the Chilean probability seminar. I was supposed to give this talk at 2017 when Manuel Cabezas invited me, but at that time I remember that I have a health problem and I have to cancel everything. I stopped to work for 6 months. So between that time and right now, I have many nice results and I can give a much more solid talk. So I'm going to speak about analytic and probabilistic number theory problems. So the plan of my talk, I'm going to begin with a short introduction to what problems we study in analytic number theory, what is the type of question we consider, and then I'm going to remember to non-familiar people the connections between prime numbers and Riemann hypothesis, and then I'm going to introduce what are the thinking about probabilistic reasoning in number theory. I'm going to speak about what people think in the last century about these things. And these connections with probabilistic reasoning, I'm going to speak about random multiplicative functions, which is the focus of this talk. And I'm going to speak about what is known about random multiplicative functions, going to review some of the known results, and I'm going to talk about a joint work with Lada Sidoravicius that I did in my PhD thesis, and some recent works with Winston Heap and Jigsaw. And this is about random multiplicative functions, a special type of random multiplicative function. And then I'm going to talk about another work, which we consider Steinhaus random multiplicative functions. And just a short introduction to analytic number theory. What you want to describe is the behavior of some arithmetic functions of number theoretic interest. So just to recall you, the Euler's phi function, the phi function of n is just the number of integers less than or equal to n that are coprime with n. So let's say, for instance, phi of 5 is 4 because there are 4 numbers coprime to 5, 1, 2, 3, and 4. And phi of 4 is equal to 2, right? Because we have 1 and 3 that are the only numbers that are less than or equal to 4 that are coprime to each other. So the phi function returns the number of integers that coprime with n. And so a classical result that we know about this phi function is that we can compute this function theoretically, and is given by this expression here. So phi of n is equal to n times the product. This bar here indicates that p divides n, so this is a standard notation number theory. So it's the product of the primes that divide n of 1 minus 1 over p, right? So a typical question that we are interested for certain arithmetic functions, the one that's this inequalities here, it's extremal values, right? So we have this extremal inequality here that holds for all n, that says that phi of n is less than or equal to n minus 1. So this inequality is optimal because when n is prime, as we see here in the case that phi of 5 is 5 minus 1, this inequality here is optimal because primes realize equality. And the opposite inequality, the lower bound, is much more complicated and is due to Mertens estimates. Which are estimates for this product here, this product, and we obtain a non-trivial estimate that phi of n is always bigger than the Euler number to a constant gamma. Remember what gamma is? The constant gamma is the limit as x goes to infinity of the harmonic numbers, sum of n less than or equal to x of 1 over n minus log of x. So this is the Euler-Mascheroni constant gamma, is given by this, and it's approximately 0.5 something. And here we have a notation that I think that is standard also for probabilists. That's little o of 1, and a quantity is little o of 1. If the limit of limit of something of f divided by g equals to 0. I don't put here what x is 10 because could be infinite, x could be 10 to a point, but it's just to describe that f divided by g converges to 0. And here this little o of 1 is, we say that when n goes to infinity. So this inequality here, what is inside this parenthesis tends to this constant f to the minus gamma times this factor here, n divided by log of n. So this is the extremal values of phi, and we are also interested in the mean behavior of phi. So the mean behavior is of phi if you sum n of less than equal to x of the values of phi. We got this constant here, 3 over pi squared, that multiplies x squared plus some error term that's fluctuates fluctuates less than x times log of x. So remember here the big O notation is, we say that f is big O of g if there exists a constant c such that the absolute value of f is less than or than c times the function g. So by this mean value here, 3 pi squared over x squared, we can conclude that the typical size of a phi of n is around n. So come back in here to the external values. This size here of a number of phi of n is much more happens less frequently than something proportional to n, the value of phi of n. And so this is the typical question that we are interested in number theory. We are always interested in the partial sums of multiplicative functions because this describes the mean behavior of an arithmetic function of interest. And so now I'm going to speak about prime numbers. So let me define the indicator function of primes by this symbol here. So indicator of primes of n equals to 1 if n is prime or 0 otherwise. And let me define the prime counting function, that is just the sum over n less than or equal to x of these indicators, right? So the prime number theorem in its stronger form states that the number of primes less than or equal to x equals this integral here, the logarithmic integral of 2 up to x of the t divided by log of t, plus an error term that cancels with x, right? So we have this cancellation here, and it's not difficult to see by L'Hopital rule from calculus that this integral here is asymptotically x divided by log of x. So we have that the number of primes satisfies this relation here, where this notation, this tilde, is equivalent to say that the limit of pi of x divided by x over log x equals to 1. So this result here is much more stronger than this one here, because here we have a quantitative statement about the error term in the prime counting function. And a classical tool to analyze these things for prime counting function, or everything about a sequence of complex numbers, is the Dirichlet series generated by this sequence. And if I call A of x the partial sums of this sequence, we have the Mellin transform, which allows us to represent the Dirichlet series as an integral of the partial sums. So f of s equals s times the integral from 1 up to infinity of the partial sums divided by x to the 1 plus s. So the Mellin transform may be regarded as a certain kind of Fourier transform, because making here a change of variables, I can write x as exponential of log of x. And so here I have s. Remember that s, I have to call here that s is a complex number equals to sigma plus it, right? And the Mellin transform after a change of variable can be seen as a Fourier transform. And we have also an inversion formula, which says that we can express the partial sums in terms of the Fourier transform, let's say, of the Dirichlet series. And here the partial sums are the integral from sigma minus infinity up to minus infinity. And sigma is any real number where the Dirichlet series converges absolutely. So we can represent these partial sums by this integral. And the important thing here is that analytic properties of the Dirichlet series transport information to the partial sums, because here is an integral, and we can show that the Dirichlet series is an analytic function. And when we have an analytic function, we have the Cauchy integral formula, where you can integrate in several ways this integral here over the complex plane, make nice approximations with the Cauchy integral formula to the partial sums. So the connection between prime numbers and the Riemann zeta function is that if you call the prime counting function as the sum of n less than or equals to x of the indicator of the primes, then the Dirichlet series is going to be only this indicator here over n to the power s, which resumes in calculate the partials, the Dirichlet series of the primes divided by p to the s. And the Riemann zeta function is classically defined as the sum over the positive integers of 1 divided by n to the s. And we have here the classical Euler product formula, that this here can be represented as a product over primes of this quantity here. And after we take the logarithm from both sides of the zeta s, we transform this product in a sum. And we can show that the logarithm of zeta of s is equal to the sum of 1 over the primes, the Dirichlet series here, plus an analytic function that is well behaved when the real part of the complex number is bigger than 1/2. So we might say that the logarithm of zeta of s is approximately the Dirichlet series of the primes. So this is why the location of the zeros of the Riemann zeta function give information about the primes, because the logarithm of a function is well behaved when this function does not assume zeros. So if there are no Riemann zeros, then we can transport information for the Dirichlet series of primes that in the previous slide I can transform. I can give information about the partial sums of a sequence by the Dirichlet series here. So here, just recall that the Riemann hypothesis is the statement that the Riemann zeta function has no zeros with real part bigger than 1/2. And so logarithm of zeta of s is well behaved. And this is equivalent to say that the prime number has this main term here, plus an error of x, where this error has a square root cancellation. So we have a power saving in the error term of 1/2. Remember that the best known result here in the previous slide, we have this x here at power on 1, right? So the Riemann hypothesis is the statement, the equivalent to the statement that this error term, we can have a power saving here in the x. And so we're going to talk about approach to the Riemann hypothesis, which is by means of the Möbius function. So the Möbius function is -1 to the number of distinct primes that divides n if n is square free. So a square free number, so for example, 6 equals 2 times 3 is a square free, but 12 equals 2 squared times 3 is not square free because it's divisible by a square. So the Möbius function is the function that is -1 to the number of distinct primes that divide n if n is square free, and equals 0 otherwise. And what we know about the Möbius function, what we would like to know is its partial sums. What is the behavior of the fluctuation of these partial sums? So an important thing is that when you consider the Dirichlet series of the Möbius function, we get the 1 divided by zeta to the s. And so 1 divided by zeta to the s, given that the relation that I explained in one of the previous slides, is the integral from 1 to infinity of the partial sums of the Möbius function. So if you assume that the partial sums of the Möbius function has square root cancellation, then I made here a simple computation where I can show that this integral here converges absolutely if this here happens for the Möbius function, for the partial sums of the Möbius function. And if this happens, if this integral converges absolutely, then as a function of s here, this is an analytic function. We can see that the absolute convergence of this integral gives an analytic function. So if this here holds, then we actually have that this implies the Riemann hypothesis, because 1 divided to zeta to the s will be an analytic function. So we cannot have zeros. Zeta cannot have zeros. Otherwise, we will have poles here for the zeta function. So the partial sums of the Möbius function being have square root cancellation, this implies the Riemann hypothesis. A non-trivial result by Littlewood in the 50s is the opposite direction, that the Riemann hypothesis actually implies square root cancellation for the partial sums of the Möbius function. So this leads to several point of views towards the Möbius function mi. So here is first value. So mi of 1 equals to 1, mi of 2 equals to -1, mi of 3 equals to -1. 4 is not square free, so mi equals to 0. 5 is only composed by 1 prime, so it's -1. Now 6 is composed by 2 primes in square free, so mi is +1. 7 is only a 1 prime, so -1. 8 is divisible by a square, so it's not square free, gives to 0. The same for 9. And 10 is divisible by 2 primes in the square free. So here we have a deterministic sequence of plus or minus ones. And at the same time that this result of Littlewood was proved, at the same time, people in probability theory was proving the first theorems about the simple random walk, where the simple random walk of S of x is just the partial sums of random plus or minus 1 signs with probability 1/2 each. One of the first results is that these partial sums have square root cancellation, which is exactly what we would like to prove for the Möbius function to establish the Riemann hypothesis. So we also know that the simple random walk does not have more than square root cancellation, because this limit sub here equals to plus infinity. And we also know that this holds for the partial sums of the Möbius function. And this result here is due to the fact that the zeta has zeros with real part equals to 1/2. So 1 divided by zeta to the s has singularities at real s bigger than equals to 1/2. And this gives this limit sup here is positive. So an argument, I think that it's around 5 years after the Littlewood proof of the equivalence of the Riemann hypothesis with the Möbius function, Denjoy said that it may perhaps be possible that M of n behave like IID random variables. So Levy, the famous Levy from probability, made an important objection to this point of view of Denjoy, that the Möbius function has an important property, which is a multiplicative function. So a multiplicative function is any function that such that f of n times m equals f of n times f of m whenever n and m are coprime. So if they don't share primes and have this property, we say that the function is multiplicative. So how we build the Möbius function from the multiplicative rule? So at the primes, we define -1, E of P of -1 for all primes P. In all powers K bigger than 2, we define me as the equals to 0. So for example, me of 30 is equal to me of 2 times me of 3 times me of 5, which equals -1. So -1 -1 times -1. And me of 24 is me of 2 cubed times me of 3, which equals to 0 times -1. So the Möbius function has this multiplicative property that from a probabilistic point of view, we can think that is somehow multiplicative dependencies on the sign pattern of the Möbius function. So let's say, for instance, if we know the Möbius function at 2 and at 3, we already know the Möbius function at 6, because 6 is equals 2 times 3. And Levy raised the question is what about can it be said for a random multiplicative function? So now instead of putting -1 at every prime as the Möbius function, we put at the primes random variables, let's say xp, assuming plus or -1 with probability 1/2 and IID. So for example, f of 30 is going to be x2 times x3 times x5, and f of 4 is going to be 0, just to have the same property of the Möbius function that is supported on the square-free integers. And after Levy raised this question, we ended up showing the 40s that the partial sums of a random multiplicative function also has square root cancellation almost surely. And this led to him the assertion that the Riemann hypothesis is almost always true. And so here I plot a simulation of a random multiplicative function. In green, I just put the value at x2 equals to -1. In white, I plot the value x2 plus equals plus 1. So at the other primes, the values are random. So I just fixed these two values for you. Observe that to change a single value at a single prime can change a lot the partial sums of a random multiplicative function. They can have a very distinct behavior here by changing only at one prime. So we have these very large dependencies with the single values that the Möbius function takes, the random multiplicative function takes at primes.
Sorry, one question. So
yes,
one basic, maybe I'm lost, but if we are just changing the value at 2, shouldn't they be equal in the odd numbers, these functions?
Can you repeat? Can you?
So one question. So this is corresponds to the cumulative sum or just to the multiplicative function?
This is the sum of
Okay.
of the
Yeah, no.
the partial sums.
Now I get it. Sorry, I thought it was the function.
Yeah.
Thank you.
The sum of the partial sums of the random multiplicative function. So you can see here that it stays above square root of x, and in above minus the square root of x and below square root of x. And we are going to see that the shape of this curve is almost like always like this. And here are some results about that Winter proved also that the exponent 1/2 is optimal in some sense for these cancellations. If we take minus epsilon, here this limit sup equals to infinity almost surely. And then this problem has been proved, these bounds, later by Erdos in the 60s, and then by Halas in the 80s. They gave significant improvements in the Winter's result. And the most recent upper bound is 2013 by Lauten and Bauen-Wu, and independently by Babaskin in 2012, that they prove that the partial sums of a random multiplicative function have square root cancellation times a log of x up to the power 2 plus epsilon, almost surely. And a very recent result of Harper from 2021, he proved that that a lower bound, an omega bound, let's say, put in this way, is almost this omega bound and the upper bound are almost correct. The only difference, they make difference from exponent 2 and exponent 1/4 here. So if you remember, we have for the simple random walk, sum of IID random variables, we have the law of the iterated logarithm. So an open question here is to determine what is the correct fluctuation of the size of fluctuation of these sums. And so this result of Harper is a very difficult result. And even before this result of Harper, we don't even know if the limit sup of the sums over the square root of x was positive. We don't know this. So this is a very important result here for this theory. And an important thing about this random multiplicative function is that this sequence here is made by orthogonal random variables. So since they are orthogonal, the size of the second moment is just the number of square field numbers less than x, which is approximately 6 divided by pi square of x times x. And an important problem in this field was Helson's conjecture that was solved also by Harper in 2017, which was to compute the size of the first moment. And Harper showed that the size of the first moment is of size square root of x divided by some cancellation log of x to the 1/4. So for the simple random walk, the moments, let's say the moments of S of x is just about the size, let me write here. For the simple random walk, the first moment is about the size of the second moment, square root and square. So the first moment is linked to the second moment by the square root, taking the square root. And you can see here that this is a very odd fact from random multiplicative functions that we don't have this same bound here. And this might explain why we see this figure here, these walks, these multiplicative walks here, always inside the region of square root of x. Harper showed that there will be infinite times that will be above this curve, but the typical size is always below, is always inside this curve, the curve square root of x. And so a corollary from the result of Harper is that we don't have convergence to Gaussian for the full sum. But there is also an interesting result from Soundarajan and Chatterjee from 2010 that a central limit theorem holds for short intervals. Let's say if we sum over a short interval, sum of n between x and x plus y with y much smaller than x, then we also have a central limit theorem. But by the result of Harper, for the first moment, if we take the full sum, let's say if we put instead of x here, we put 1, then we don't have central limit theorem. So it's a very odd behavior for these sums. And okay, so I explained here to you some features of a random multiplicative function. And now I want to explain my first result jointly with Vlada Sidoravicius is that if we can obtain, we consider the question that if we can obtain a direct connection between this random model with the Riemann hypothesis. And so what he proved is that with perturb, let's say, the Bernoulli random variables, let's say probability of xp equals to -1 is a little bit biased towards -1. Let's say with this kind of bias here, then the partial sums have square root cancellation if and only if the Riemann hypothesis holds, this for every alpha on this bias here. And just in contrast to this, if instead put this bias, observe here that this term here converges to 0. So we are close to the unbiased case. But if we put a strong bias, let's say a parameter beta, with beta bigger than 1/2, less than 1, then we can show that the sum has no cancellation at all. Is not big O of x to the 1 minus epsilon for any epsilon. So it has no cancellation at all. Remember that the Möbius function corresponds here to the case beta equals to 1, which is the deterministic case where all the values of fp at prime is equals to -1. So it's a very odd behavior. And so an open question is to, as I said previously, is to obtain the true size of fluctuation of these sums. So a related deterministic question that is more from a number theoretic side is if there are deterministic way to choose the values xp equals to plus or minus 1 to produce a multiplicative function with small partial sums. So I considered this question, and in 2017, I showed that exist several choices of xp at primes, right? Plus deterministic choice of the values of plus or minus 1, for which the partial sums have more than square root cancellation. And further, in the same paper, I proved that if you assume the Riemann hypothesis, then these examples actually have more than square root cancellation, has a power saver here in the exponent. I think that 2 5s is equals to 1/2 minus 1/10. So we have this -1/10 here. That's a big power saving in these examples. So in this problem, I believe that the exponent 2/5 can be replaced by 1/4 in my examples, deterministic examples. And Liu in 2022, building inside my work, improved the exponent 2/5 to 1/3. And a different question that I proved in 2019 is that all choices, no matter how you choose the values xp at primes, you always end up with the partial sums unbounded. The limit super of the partial sums will be plus infinity. And this kind of result here is related to the Erdos discrepancy problem that has been solved by Tao in 2015. So my conjecture for this problem is that for all of these choices of xp, we always don't, we will not have more than x to the 1/4 cancellation. So this limit super of the partial sums will always be positive of the partial sums of f divided by x to the 1/4. This is my conjecture. And so other kind of question about this random multiplicative function that we consider is that what properties of the trajectories that I put in the graphic. A question that we consider is that if this random walk that walks multiplicative with the multiplicative rule goes back to the origin infinitely often. And we know that for the Möbius function, this is true. The partial sums of the Möbius function will come back to the origin infinitely often. And in a work jointly with Hipp and Zhao, we proved that for every integer z, the partial sums equals to z infinitely often almost surely. So this walk is recurrent in Markov chain language. And now I'm going to comment the proof of this recurrence, because I think that is one of the most simplest proofs in the field. And I think that's very explanatory, the kind of tools that we use. So again, here we start with the Dirichlet series that can be expressed as an integral of the partial sums. And just as the Riemann zeta function, any multiplicative function has the Dirichlet series has a representation as an Euler product. And an Euler product, this product here is nothing more than the explanation of a sum. So I here take the first sums that define this Euler product is the sum of independent random variables, a random series here, minus a deterministic sum, plus some correction function, a well-behaved function, when the number s, remember that s equals to sigma plus it, and the real part sigma is bigger than 1/3, the real part of s. And if you recall basic probability theory, sum of independent random variables converges almost surely by Kolmogorov two-series theorem, and is well behaved when s has real part bigger than 1/2. This is given by the Kolmogorov two-series theorem. So this here to this series we apply the Kolmogorov two-series theorem. And this sum here that I was explaining in the previous slides, this is approximately the logarithm of the zeta function, the Dirichlet series of the primes. And when s is close to 1/2, 2s is close to 1, and this behaves like the logarithm of 1 divided by 2 to the s minus 1. So in a previous work with Ricardo Mesturi and Susana Frometa, we studied the random sums given by independent random variables. Let's say sum of independent random variables divided by n to the sigma, sigma is real. And we proved a law of the iterated logarithm for this random series. So when sigma approaches to 1/2, we have this kind of explosion here for the random series. Is this kind of rate of the fluctuations of this series. And so this we proved when you sum over all integers, but I don't know how to prove for primes, but I know that the proof of this result at least give this bound here, that the sum of the series of the primes over p to the sigma is bounded by log of this quantity here to the power 1/2 plus epsilon. So what this tells to us, coming back to the representation of the Dirichlet series, this is the exponential of the square root of this logarithm, and this term here behaves like this, and so this term here is winning in this competition with this term here, because here we have exponent 1/2, and here we have exponent 1. So this converges to exponential of minus infinity that equals to 0. So what we learn from this is that f of sigma converges to 0 as sigma approaches to 1/2 almost surely. So this translates that this integral here of the partial sums converges to 0. So now you may think you have an integral of a function over the real line converges to zeros. This gives hints that this function must at least change sign at least one time. But this is not enough, and we have to show that actually, let me go to another slide, that we have to show that the sum of the absolute value goes to infinity. And if you have these two things here, then this gives infinite sign change, because think of this, or you have a function on the real line, and you integrate the absolute value of this function, this is infinity. And without the absolute value, this integral converges to 0. So this must force infinite sign changes for the function that you are integrating. So this is how we prove the infinite sign changes for the partial sums of a random multiplicative function. And since we have infinite sign changes, and since the sums always jumps from at most step 1, it always walk in integers. So this gives that it must come back to the origin infinitely often. And so an open question that we are working now is the arithmetic walk in 2 dimensions. So now at primes, instead of assuming only plus or minus 1, now you put plus or minus I. The I is the square root of minus 1, is the unitary imaginary number. So a question that we are considering if this walk is infinite, come back to the origin infinitely often, and seems to be a very, very hard question. And another kind of model that we can consider for these multiplicative functions is that instead of taking plus or minus 1 at primes, now we choose a random number in the unit complex circle of modulus numbers with modulus 1. So we have here xp equals to e to the 2 pi I theta p, where theta p is uniform in the interval 0, 1 and IID. So we are choosing points in the unit circle independently. And so we consider f of p equals to x of xp, and now we define a multiplicative function such that f of p1 at alpha 1, etc., pk at alpha k equals to f of p1 at alpha 1, etc., times this product. And this leads to a completely multiplicative function that differs from only multiplicative, because the multiplicative property needs to hold only for at least for numbers that are coprime. And completely multiplicative means that f of n times m equals f of n times f of m for all n and m. So this function has this property of completely multiplicative. And we call this function f as a Steinhaus random multiplicative function. And this can be regarded as a model for the deterministic function n to the power it, because n to the power it is also a completely multiplicative function that assigns for each product of primes this value here, that can be rewritten at exponential of e of the powers of log of the first prime, etc., e alpha I alpha k times t times the log of the pk prime. And these numbers here, the numbers log of p, they are linearly independent over the rational numbers because they're unique factorization of numbers. And so we can think that the Steinhaus random multiplicative function can be a model for n to the it, right? Because the numbers a it log p should behave like a random number in the unity circle. And why this is good is because the Riemann zeta function at critical line, at the line 1/2 plus it, can be approximated by this function n to the power it divided by square root of n. when this number t here is large between capital T and 2 capital T, the geodic interval. So we can think that the partial sums of a Steinhaus random multiplicative function could be seen as a good model for the zeta function at the critical line. And many information about the zeta function in the critical line give a lot of information about prime numbers and lot of other number theoretic things. So a kind of interesting question about the zeta function at the critical line is Selberg's central limit theorem, which says that the Riemann zeta function at the critical line satisfies a certain kind of central limit theorem described by these equations here. So here Leb is Lebesgue measure. And there is a famous conjecture by Farmer, Gornick, and Hughes, which describes how the maximum behavior of the zeta function is at the critical line, which is the maximum bit of t between capital T and 2 capital T is the exponential of 1 plus little o of 1 times the square root of 1/2 times log of t times log of t. And they arrived at this conjecture by modeling the zeta function by a heliometric theorem. And here I think I would like to explain a thing that I think I will jump this slide here. But this slide the previous slide was to explain this claim here that we might expect that by sampling t times log of t points independently, one can pick up the maximum of the zeta function of 1/2 plus it. So we take the t log of t points, let's say a random point process in this interval. We take t log of t primes, then we can pick up the maximum of the zeta of 1 plus it. And these heuristics, we consider these heuristics in a paper with Hippie and Zhao in 2021, that if we sample t of log of t independent Steinhaus random multiplicative functions, then we verify the Farmer-Gornick-Hughes conjecture for this random model in probability. So the probability that the maximum of these random sums, these various sums of Steinhaus random variable, satisfies the bound of the Farmer-Gornick-Hughes conjecture if this epsilon here is positive, right? And if the epsilon is negative, then the probability becomes near to O of 1. So this is somehow in agreement with the random matrix theory prediction by the conjecture of Farmer-Gornick and Hughes. And in the same paper, we also considered almost sure bounds for these random sums, and we proved that these random sums here have log of t cancellation to the power 1/2 square root cancellation of the log of t of the variance. We proved this bound, and concerning the lower bounds, we proved that this limit sup here of exponential of L times square root of log of t, this limit sup equals to infinity. So we can see that this quantity here is much smaller than log of t to the power epsilon for any epsilon positive, right? So we have a considerable gap between our upper bounds and our omega bounds. And we conjecture that the lower bound is the correct one because we have the moments have more than square root cancellation, the moments of the low moments of these partial sums. And I'm going to give a few ingredients that we use to prove this upper bound. And this upper bound is done by controlling the fourth moment. So the fourth moment of short sums of intervals of this Steinhaus random multiplicative function is bounded both by the divisor function tau of n divided by n, where the tau of n is the number of divisors of n. And we know a result from number theory that the partial sums, the average of the number of divisors of n is given by this expression here. And the most important thing that we use in this ingredient is that the error term here satisfies a cancellation better than square root cancellation. Here you have minus epsilon. So this is a very important ingredient. And another important ingredient is an inequality from the book of Billingsley, from the famous books of Billingsley that all of we study in graduate courses. And this inequality says the following: if you consider any set of random variables, they don't need to be independent. So S of n is the partial sums up to n of these random variables. And if you have an exponent alpha bigger than 1/2 and beta bigger than 0, and if u1 and un, etc., are numbers such that this inequality here holds for every short sum, j and I can be close to each other, and we can control this probability by this sum here, then we actually have a maximal inequality for the partial sums, for the full sum. So the key ingredient here is that this, in our approach, we make this alpha tends to 1/2, so this exponent 2 alpha tends to 1. And concerning lower bounds, we proved building on Harper's solution of Helson's conjecture, the first moment that I talked previously. We actually, if we consider v of this size, L times square root of 1/2 times log of t, then the probability of these partial sums being larger than exponential to the v has a Gaussian lower bound. And so we can also show that the event where this sum is large is a tail event. This is not so easy to see because, okay, if you take a prime, if you change the value of prime, you change all the history of the partial sums, right? So it's not clear that this will be a tail event, but because we have here this square root of n, this for large numbers, these changes, small changes in the first values of primes, this makes somehow a finite number of changes because we are putting this right here, makes this a tail event. And so we can show, so if it's a tail event such that this probability is positive, so actually must have probability of being large must be 1, right? The Kolmogorov 0 or 1 law. And so I'm marking here 51 minutes. I think that the talk was 55, right? So thank you so much for listening to me. I will be happy to answer questions if you have anyone.
Okay, Marco, thanks for the talk. Let's thank Marco yeah. So are there any questions? Oh, okay. So I have a question, Marco. At some point, you mentioned that there's a connection between this and multiplicative chaos theory.
Yes. I think that I forgot to talk about this, but the multiplicative chaos theory are different words, right? The multiplicative in probability theory has a meaning, and in number theory has this meaning here. But yes, let me see this slide here. Is Harper's solution of Helson's conjecture. Yes, here. The way that Harper solved this problem, computed this first moment, he actually used several tools from multiplicative chaos theory that was developed by, if I remember correctly, Remy Rhodes and Vincent Vargas, and everything of this has to do with that these other products here, let's say product of 1 plus f of p, p to the sigma, this is just the exponential of sum over primes, essentially. And exponential of sum over primes leads to logarithmic, let's say logarithmic correlations or something like this. I'm not a specialist, actually I'm not a specialist in multiplicative chaos theory, but this is somehow it connects because the other product.
Okay. 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 So are there any other questions? Okay. If not, then let's thank Marco again. Later.
Okay, I would like to thank you for the opportunity to give this talk. I have been in Chile 2 times, and all the times that I have been in Chile, I love it. Very good wine. And I remember that there was some schools that were organized by Alejandro Ramirez and Vladas Doravicius. And I remember, and Chuck Newman from NIU. And I remember that at some conference, they took us to the Undurraga wine factory. It was very nice time, very good wine.
So when was this? Which year do you remember?
I think that was, well, a good year, right? That we have plenty of money from doing conference. I think that was 2009, 2011, perhaps.
Yeah, I think I was there too, but maybe 2010 or 20, around that time.
Yeah.
But I didn't go to the vineyards. Anyway.
Yeah.
Okay, let me stop the recording and